Hello everyone! Today let's talk about a core tool in semiconductor testing, the RF probe. With the rapid growth in 5G, millimeter wave, wafer chip testing, and RF device testing, the RF probe has become the most important bridge between instruments and chips. In the R&D or testing of RF, millimeter waves, and terahertz devices and modules, RF probes are used throughout multiple stages, such as model extraction, validation, and mass testing. Because it can perform direct contact measurements on bare dies or packaged RF nodes, it improves accuracy and efficiency, helping engineers find issues early and shorten cycles. During on-wafer testing, it transmits the signals from the test instrument to the chip. It converts coaxial or waveguide modes into coplanar waveguide (CPW) modes on the chip. The probe tip plays the role of mode conversion here. Simply put, the RF probe delivers the signals to the DET cleanly and stably. The quality of the probe determines whether you can see the real signal clearly. Traditional RF probes consist of 1. An interface to the instrument, varying by frequency. Common connectors have different frequencies such as 2.9 to millimeters, 1.85 millimeters, 1.0 millimeters, etc. For higher millimeter wave, terahertz bands, waveguide ports, or specialized transitions are used. 2. Probe housing. 3. Coaxial cable. 4. Coaxial two-tip transition structure. 5. Probe tip. Among them, the tip represents the pinnacle of various fields. How to control its electrical performance to an impedance of 50 ohms. How to improve its conductivity chemically through surface treatments. And how to achieve micron-level precision in machining. Therefore, the tip is the greatest challenge and the key direction to break through well-known brands. Technical barriers. Common tips. ACP used by many Chinese brands, GGB's Pika probe, and Cascade's Infinity. Mechanically, a probe must provide controlled contact force to reduce resistance and loss, while having good elasticity and wear resistance for a long service life. The tip wears down against AL or OPADs. The probe itself is also fragile. It can be damaged by improper use or low stage accuracy. It is both an instrument and a consumable. Standardized use and maintenance are mandatory. Tip materials and structures vary based on different pad materials and sizes. For gold pads, beryllium copper is common to balance conductivity and wear resistance. For aluminum pads, tungsten or hard materials reduce oxidation and adhesion issues. In PCB testing, ACP air coplanar tips are widely used for durability and cost advantages. The ACP structure is usually formed by stamping vacuum sheets and welding them onto coaxial lines. Taking Dzinken as an example, tip widths come in 25 micrometers and 50 micrometers. When pad pitch exceeds 300 micrometers, a 50 micrometers tip is used for better durability. In small pitch scenarios, 25 micrometers is more suitable for fine contacts. When pads reach the tens of micron scale, geometric precision requirements are very high. High-end wafer probes can achieve machining accuracy in the 10 micrometer range. For example, Dzinken's blade probe has a tip width control to about 10 micrometers. It can meet the strict testing requirements of wafer and chip levels. The blade probe adopts a circular coaxial structure similar to Pika probe. The center conductor forms the tip, and the outer conductor forms the ground via a Beckett collar. This structure allows smaller pitches, e.g., blade probes can reach 40 micrometers pitch. This maintains good contact and accuracy in small pads and dense layout scenarios. Emergence of the blade probe, so that the Chinese probe is no longer limited to a single ACP structure. It provides more high-performance solutions and is a major breakthrough in Chinese technology. In our actual testing, probes, cables, and adapters introduce parasitic reflections, phase shifts, and attenuations. Without eliminating these, you don't get the true S parameters or impedance of the device. Instead, you get a composite result including probe link errors. Calibration and de-embedding ensure credibility. Calibration uses corresponding substrates, e.g., SOLT, TRL. De-embedding uses factory S parameter files provided by the vendor, S to P. S for P files to perform de-embedding on the vector network analyzer. Only after this can probe influences be removed from the final data, allowing for a true and reliable assessment of chip or device performance. To summarize, the RF probe connects instruments to the chip world, determining whether we can see the true performance of high-frequency signals. If you need RF probes, feel free to contact me. We offer both ACP and blade tip solutions. We support up to 110 GHz with fast delivery and customization support, helping you validate device performance reliably and efficiently. Thanks for watching.